Hi, everyone. We're going to wait until we get a few more people to join, and we will start at the top of the hour. And thanks, everybody, for jumping in here, and give us a couple of more minutes, let some people come in, and then we will start going. Thank you. Well, good afternoon and evening, everyone. Thanks for joining us. It's the top of the hour. We're going to kick this off. Welcome to AFL's Fiber Optics Demystified, OTDR's Fundamentals webinar. I'm Charlie Collius, the Global Product Marketing Manager for the Equipment Group here at AFL. We're delighted to have you all here today to dive into the basics of fiber optics and explore the critical role that OTDRs play in testing and troubleshooting. But before we begin here today, I just want to go over some housekeeping tips. All attendees here are in listen-only mode to reduce background noise during this webinar. Throughout today's presentation, please feel free to submit any questions you have using the questions box in the control panel on your screen. We'll answer these at the end of the presentation, so don't hesitate to ask during the session. Just type them in right there. Today's webinar is being recorded and should last about 50 minutes. A link with where to view the recording will be sent out tomorrow, along with a certificate of completion. This session is the first part of a two-part webinar series focused on OTDRs. The second webinar, titled From Glitches to Glory, OTDR Problem-Solving Strategies, will take place on April 23rd in about a couple of weeks. An email reminder will be sent to you next week with the registration link if you haven't registered already. So right now, it's my pleasure to introduce Michael Scholten, who is our presenter today. Michael is a Senior Product Line Manager for OTDRs here at AFL. He has over 20 years of experience in fiber optic network test, including product marketing, systems engineering, project management, hardware, software development. Quite a background. Michael, whenever you are ready, go ahead and take it away.
Great. Thank you very much, Charlie. Good afternoon, good morning, good evening, wherever you are, and welcome to our presentation. So quick outline. I'll start with some characteristics of fiber optic networks, so attenuation, reflections, Rayleigh scattering, and Fresnel reflections, wavelength-dependent fiber loss, bend-dependent fiber loss, and a little bit about connectors and splices. With that background, then we'll jump into an overview of OTDRs, theory of operation, how do they work, why use one, when and where to use one, and then continue into OTDR test settings and OTDR performance, what is dynamic range and dead zone, how your settings affect that, automatic, expert, and real-time test modes, and then a little bit about setting range, pulse width, and averaging time. We'll continue with interpreting an OTDR trace. So look at the trace, How do you measure link length, loss, and ORL? How do you locate and measure events? What's different about a trace when you have PC connectors versus angle polish connectors? What do fusion mechanical splices look like? How do macrobands and microbands show up? And what about splitters? Then we'll jump into interpreting the OTDR LinkMap and its event table, and then wrap up with saving, downloading, and reporting results. So let's begin with fiber optic network characteristics. So this is important because there are certain factors which really do affect fiber optic network performance. What are those? And the key optical network factors are received power level and optical loss through the network, reflections in the network, and then chromatic dispersion and polarization mode dispersion, CD, PMD. So how do low power, excess loss, excess reflection, and dispersion impact performance? Well, any of these can degrade optical system performance. When I say degrade, it means that bit error rate increases, or if you're operating a packet-based network, an IP or an Ethernet-based network, packet loss and retransmission increases, reducing your overall throughput. When those excess loss or reflection reach really critical levels, then communication can fail. The signal can be lost. The receive power can be too low for a receiver to actually synchronize on the signal and recover the data from it. So what to do when system performance degrades or fails? First thing would be check your system power levels. Is your transmitter putting out an appropriate level? If it's absent or too low, replace the optical transmitter. If the receive power level is too low, but your transmitter is putting out adequate power, then there must be excess loss in your optical network. And if the receive power is okay, but you still have degraded performance, check for excess reflections in your optical network. And then lastly, if no excess reflections and you're operating on a very high-speed network, then you may want to check for chromatic dispersion or polarization mode dispersion. So what are the primary causes of optical network failures? A few years ago, NTT ran a survey, and what they got back from cable installers and network installers was contamination of the connector end face, or poor polishing of the ferrule, or dirty or damaged connectors, and defective splicing. So it's physical impairments on the in the optical fiber network that are the major causes of optical network failures. So let's look a little bit more in depth at those. Dirty, damaged, or mismatched connectors. To prevent that, you always want to clean your connectors before mating. You never want to mate a UPC connector, which has a 90-degree angle, to an angle polish connector, because you will create an air gap at the where those two connectors meet. And there's always a reflection at a glass air interface, and that reflection on a UPC connector will be guided back up the network, potentially causing re-reflections, and can be a source of bit errors. You want to make sure your connectors are fully seated in their bulkhead adapters, and you want to replace damaged connectors with factory polished connectors, such as the fuse-on fuse connect, or the mechanically spliced on fast connect. How do you know if you have dirty or damaged connectors? Well, you need a connector inspection probe for that. We won't delve into that today, but just be aware that that's how you would inspect it. And we have lots of cleaning tools available to remove contamination. Poor splices are another source of optical loss in the network. So when you are splicing, make sure you strip, clean, and cleave in that order. So your cleaving should be the last step. Clean and maintain your fusion splicer. Make sure you rotate your cleaver blades when they're worn, because a worn cleaver blade will produce poor splices, poor cleaves that will then not splice well. And then splice alignment. So core alignment machines produce better splices than cladding alignment. Cladding alignment works on the outer diameter of the fiber, whereas core alignment actually images the core through the center of that fiber and does the best alignment based on the core. Fiber breaks are also a source of optical loss. The so-called backhoe fade, when someone's dug up your underground cable. Squirrel chews, rodents or other animals chewing on your fiber and damaging them. And then maintenance activity, which may produce an unintended disconnect inside a cabinet. Additional causes of optical loss in fiber networks could be fiber loss due to Rayleigh scattering. This is the primary source of loss along the full length of the fiber. And typically the loss per distance is higher at 1310 nanometer wavelength than at 1550 nanometer wavelength. The longer the wavelength, up to about 1550, the lower, as you can see, the lower the loss will be. As you can see in the graph in the lower right, there are some water peaks, and modern single mode fiber has been modified to reduce the loss due to water peaks. Captured backscatter light is used by the OTDR to measure loss. You can also have loss in your fiber due to microbands or macrobands. Microbands occur due to cabling when the pulling actually stresses the fiber. It could also occur due to environmental stress. If you get water in your cable and then it freezes, it puts pressure on the fiber and will create these microbands. Macro bends are due to tight bends, typically in cabinets and splice closures. And bending loss increases at longer wavelengths, so you will see a more dramatic effect bending loss at 1550 nanometer than you would at 1310. And you'd see even higher bending loss at 1625 or 1650 nanometer wavelengths, which are often used to test live passive optical networks, FTTH networks. Tighter bends do create higher loss, as you can see in the graph in the lower left-hand corner. Reflections in optical networks. Fresnel reflections occur due to a mismatch in the group index of refraction. Glass and air have different indices of refraction, and that's why you always get a reflection at the glass-air interface. The difference in the index of refraction results in approximately a 4% reflection at that glass-air interface. And if you were to measure the reflectance, it would be about minus 14 dB due to that glass-air interface at a perpendicular interface. A slight index of refraction mismatch between polished and unpolished glass causes a small reflection at mated connectors. And again, if that's a right angle connection, a 90-degree end face, then some of that reflection will be guided back up the fiber. With APC connectors, you still get that 4% reflection, but the angle on the end connector is designed to exceed the capture angle or the critical angle of the fiber, so that reflected energy does not get guided back up the fiber. If you have some poor connections in your network with high reflections, then you can get multiple reflections in your optical network. reflection from one connector re-reflects off a previous connector, and you get a smaller ghost image of the previous transmission, and that increases the noise in your transmission signal, degrades your signal to noise ratio, and can increase your bit error rate. This typically is a bigger problem at higher data rates, in part because your digital eye closes up. You have a less signal to noise ratio to begin with. As people go to advanced modulation schemes, such as QAM or PAM, that also reduces the eye, and those modulation schemes will be more sensitive to a poor signal to noise ratio. Preventing reflection. So the key to preventing reflections is make sure you inspect and clean your connectors before mating. Any dirt on the connector when you mate it is going to get ground into the end face of the connector you made it to, and once you've damaged that end face, no amount of cleaning is going to repair that. And then lastly, never mate PC or UPC blue connectors to angle polished green connectors, because it will create that air gap. You will get an excess reflection off the perpendicular end face of the blue PC or UPC connector. And then make sure you do terminate fibers with factory polished connectors that are readily available today. You can do field polishing, but if you do, you need to make sure the epoxy is fully cleaned and polished off the connector end face, and don't over polish it, because doing so can create the dimple in the fiber core, as it's typically softer than the cladding and the ceramic ferrule around it. So how do you measure end-to-end length and insertion loss? Well, the insertion loss is the sum of all losses through the network. So you may have multiple splices, multiple connectors in your network, and each of them introduce loss as well as the fiber itself. You can most accurately measure the insertion loss of the network under test using a light source and a power meter. In this case, you inject light using the light source, and you measure what comes out using the power meter. The difference between the input power and the output power is your insertion loss. And if your input power is measured in dBm, dB relative to a milliwatt, and your output power also measured in dBm, the difference between them will be the loss in dB or decibels. Advantages of insertion loss measurement using a light source and a power meter is a very simple, very fast pass-fail test. When I say pass-fail test, you typically have a loss budget that's been calculated prior to installation. If your loss exceeds that loss budget, it would be considered failing. If your loss is less than what you calculated for your budget, it would be passing. If your loss exceeds the loss budget, a drawback of the light source and power meter is it cannot identify or locate the sources of excess loss. Additionally, a loss test using a light source and a power meter is typically a two-ended test requiring two people, one at each end of the network, one equipped with the light source, one equipped with the power meter. And if you're measuring at more than one wavelength, then typically 1310 and 1550 are used to measure loss on single mode networks. You may also need to coordinate between the user of the light source and the user of the power meter to switch wavelengths, unless you have a wave ID capability, such as we include in our light sources and power meters, which supports testing 2 wavelengths or even up to 3 wavelengths at once. Insertion loss and length can be measured length can be measured more accurately than with the light source and a power meter, and insertion loss can be measured nearly as accurately as an OTDR. Significant advantage of the OTDR is that the testing can be completed by one person with access to just one end of the network. Additionally, the OTDR can identify and locate the sources of excess loss and reflections because it gives you a trace of the fiber. There are spikes that show up where you have reflections. There's a drop in the backscatter level where you have splices or macrobands. However, an OTDR is a more complicated instrument than a simple light source and power meter, so it requires a more skilled technician. So let's get into OTDRs, start with the theory of operation. So an OTDR, I think of it as a one-dimensional optical radar. It injects pulses of light into one end of the fiber and then measures the amplitude and time of flight for backscatter and reflections to be guided back up the fiber as that pulse transmits down the fiber. The software inside the OTDR converts time of flight into distance based on the speed of light in glass, which is determined by the index of refraction. And then it will plot the return signal level or loss in dB versus distance after converting time to distance. With that, we can measure the loss of fiber sections, the end-to-end loss, the loss and reflectance of the mated connections in the network, the loss of splices, or the loss of macrobands or breaks. So key advantages here, again, it's a single-ended test. It identifies and locates the sources of excess loss and reflections, but it is a more expensive test set, requires more user skill, and the loss measurements are slightly less accurate. And that's because it's determining loss based on backscatter rather than the light that's actually injected in one end and measured coming out of the other end. Some key parameters of OTDRs include dynamic range and dead zone. So when people go to select an OTDR, this is one of the first specifications they'll look at. So key questions are, what is dynamic range and how does that relate to how long a fiber can I measure, or how much loss can I have in my network? So dynamic range, it's an OTDR specification that summarizes the difference in dB between the initial backscatter level and the peak or the RMS value of the noise floor. So once the light exits the fiber, you only get noise coming back, or you're only measuring noise. And you want your backscatter level to be out of the noise in order to be able to make measurements at the end of the fiber. Dynamic range depends on pulse width and depends on averaging time. Wider pulse widths increase the dynamic range, and longer averaging time reduces noise, so it also increases dynamic range. How do I turn that into something that's useful to me? Well, what I care about is how much loss can I have in my network. So what's my loss measurement range based on dynamic range? And a typical way to think of it is take the dynamic range, subtract 6 dB off it, and that will give you your loss measurement range. It means that at a loss measurement range that's 6 dB less than the dynamic range, I can reliably detect an end. I should be able to measure a ½ dB loss event at that point. So next question is, well, what's the distance measurement range? And this is a harder question to answer because it really depends on the loss through your network. Now, typical networks, single mode networks, are considered to be acceptable if their loss per distance is no more than 0.5 dB per kilometer. So if I was to take my loss measurement range and divide that by 0.5 dB per kilometer, that would give me a reasonable estimate of my distance measurement range. Now at longer wavelengths, you recall I indicated that the loss per distance is lower. So on 1550 nanometer networks, you may be able to go further than you can. You certainly should expect to be able to measure further down a long fiber at 1550 than at 1310. And you're not as likely to have a 0.5 dB per kilometer. It may be more like 0.3 dB per kilometer at 1550 nanometer, assuming you have good splices through your network. So what is dead zone? This is another spec that OTDR engineers would use to specify, or end users would use to select it. So event dead zone indicates how close two reflective events, typically two connectors, can be. And the peak reflection or the spike reflection from both of those can still be visually detected. Attenuation dead zone is really a measure of how closely a small non-reflective event can be visually detected following a reflection. And when you get into the details, the OTDR vendors will specify how big is that reflection before the event. Telcordia standard is minus 45 dB for the reflection, but we've seen some OTDR manufacturers pick a more relaxed reflection amplitude so they can quote a shorter attenuation dead zone. For event dead zone, it's also, typically two minus 45 dB reflectance events close together. As with dynamic range, the dead zone depends on pulse width. In the case of dynamic range, a wider pulse width is better. You get more dynamic range with a wider pulse width. You'll get a better signal to noise ratio with a wider pulse width. The opposite is true with dead zones. With wider pulse widths, two closely spaced events will begin to overlap. And so you want to use a narrow pulse width to have narrow dead zones, but when you do that, your backscatter level will fall closer to the noise floor, and you won't be able to test as far down the network. So here we have the case that wider pulse widths increase dead zone, but reduce the ability to independently detect closely spaced connectors and splices. So let's talk a little bit now about OTDR test settings and performance. So virtually all OTDRs today offer an automatic mode. In our FlexScan family, we call it Smart Auto. And it automatically sets the range, the pulse widths, which we use in Smart Auto mode, and the averaging time. Benefits are that it prevents users from selecting inappropriate settings. This is especially true for novice users, less skilled users. It typically will complete the test at both the 1310 and 1550 nanometer wavelengths for an out of service or a dark fiber. It may also automatically complete a test at 1625 or 1650 nanometer on a live PON network. And those wavelengths will be used because they're out of band with respect to the operational wavelengths that are used to send traffic up and down the PON network. Newer OTDRs will have what's called a multi-pulse acquisition that allows automatic tests to be completed using a combination of narrow, medium, and wide pulse widths. And this gives you, in essence, the best of both worlds. With the narrow pulse widths, you can get the short dead zones. With the medium and wider pulse widths, you'll have enough dynamic range to see further down the fiber and detect events, the faults further down the fiber. You may not be able to test short range on a long fiber in automatic mode, as well as you could with a expert mode using a single fixed pulse width. And it may take longer to test short fibers because it's automatically using these multiple pulse widths and taking a little bit longer to perform enough averaging at each of those pulse widths. In expert mode, the user manually sets the wavelengths, the range, the pulse width, and the averaging time. This allows the user to tailor the settings for best performance on a specific region of the fiber. And in the case of very short fibers, you could reduce the test time by using, a single appropriate pulse width with shorter averaging time. Drawbacks here are poor test settings will produce poor results. For example, if you used a wide pulse width on a short fiber, you may have overlapping connections and you aren't able to see those as multiple events. And conversely, if you picked a very narrow pulse width on the longer fiber, the trace may drop into the noise floor before you reach the end, or the trace can get very noisy before the end and miss some events. So it can confuse a less experienced user. And then lastly here, testing at a single wavelength will not detect macrobands. Macrobands are detected by comparing the loss of events at a short wavelength to the loss of the same events at a longer wavelength. For example, compare the trace you get at 1310 to the trace you get at 1550. And typically, if the event loss is 0.2 of a dB or more at 1550 than it is at 1310, we would declare a macroband at that location. And this is important to know. Macrobands typically occur at connectors and splices because you've bent the fiber, wrapped it too tightly in a splice enclosure or inside a cabinet. And you see a high loss at a splice point. If that high loss was due to a macroband rather than the splice, you might, break the splice, resplice it, but you haven't fixed the problem. You haven't corrected the macroband. And the same thing can occur at a connection point inside a cabinet. Lastly, real-time mode. So real-time trace updates with little averaging. So your averaging time might be a second, 2 seconds, or less. This allows the OTDR user to verify that the fiber under test is the fiber a user out in the field is actually working on. And the way you would do this is the user out in the field would intentionally bend the fiber, and you as the user at the end of the fiber would be looking for an increased loss at the distance where that user in the field is located. If they're bending the fiber and you're not seeing the loss increase, then you're not testing the same fiber that they're bending. It also allows users to determine if a mechanical splice has been optimized for minimum loss and reflection, and they could adjust that mechanical splice until you see minimum loss and reflection at that point. Real-time mode does not automatically analyze and evaluate events, and it does not save the results. Whereas in automatic mode and expert mode, when a test is complete, you can manually or automatically save the results, and analysis software would be run to identify and locate the splices, the connectors, the splitters, the macrobands, and save all of that in what's called an SOR file, from which you could generate the report or review the results or provide this SOR file to someone else to review. In expert and real-time mode, you have control over range, pulse width, and averaging time, as well as the wavelength. So how do you know what an appropriate range selection is? So if the range is too long, the end and events will be found, but your trace will be compressed at the start. You'll have lower resolution since the data spacing is probably increased because of your long distance range, and your dynamic range may be reduced since the number of averages is reduced the longer the fiber is that you are testing, assuming a constant averaging time. If the range is too short, then you won't see the end of the fiber. And in this case, the end of the fiber is beyond the end of the trace as we can see it on our OTDR. With short range, you can use shorter pulse widths, and you'll get good signal to noise ratio in that short range, but you'll miss the end of the fiber. And if your range was too short and there were reflections beyond the end of the image range, you may alias reflections that occurred beyond the end of the fiber, and they may appear as if they're in the short section of fiber that you're testing, and may lead you to believe that you have some events where there actually don't exist. And if the range is just right, then the end and all events will be found. Our kind of rule of thumb is pick a range that's at least 20% longer than the network that you're testing. And do make sure if you're using a launch cable, we'll talk a little bit more about that in a minute, or a tail cord or receive cable, that you include the length of the launch cord and the tail cord in your estimate of the total length of the network being tested. So manual pulse width selection. As I had mentioned, narrow pulses reduce your dead zone. So this can prevent closely spaced events from overlapping, and it allows closely spaced events to be independently detected and measured. However, the backscatter level is lower, and that reduces your measurement range. So in the graph here, I've shown you a comparison of what a 30 nanosecond pulse width looks like. That's the red and the black pulses representing 1310 and 1550. And I've also shown you what a 5 nanosecond pulse width looks like at a reflective event. And those are the green and the blue traces, green being the 1550 nanometer at 5 nanoseconds and blue being the 1310 nanometer at 5 nanoseconds. With this, you can see that the 30 nanosecond pulse width will be longer than 3 meters or 10 feet. And so if you had two connections that were, let's say, only 2 meters apart, they would overlap in the reflection from the first connection, and it would extend out that peak due to the reflection before it dropped back down to the backscatter level. With the 5 nanosecond pulse width, the peak is only a half a meter wide, and so you'd easily be able to see two events, 3 meters apart or 10 feet apart. So some rules of thumb here, pulse width and dead zone. Typical rule of thumb is that the round trip speed of light in fiber is about 10 nanoseconds per meter. And that means that a dead zone from a 10 nanosecond pulse width will be greater than or equal to 1 meter of fiber. So if I looked at 100 nanosecond pulse width, that's going to be greater than 10 meters. If I looked at a 1 microsecond pulse width, that means my dead zone will be greater than 100 meters, or greater than 300 feet. Wider pulses do increase dynamic range. They raise the backscatter level and pull it further out of the noise. And that's what allows us to find the events in the end on longer fibers. If you double the pulse width, that will improve your dynamic range by approximately 1.5 dB. That also allows you to generally make more accurate loss measurements on splices and connectors. However, the drawback is it causes these closely spaced events to overlap, preventing independent event detection and measurement. And you can see in the graph here that the backscatter level of the red and black traces is higher than the blue and the green 5 nanosecond traces. And the signal levels are cleaner, less noisy than what you see in the blue and the green signals. So manual mode averaging time. Short averaging time produces noisy traces, but reduces your test time. Noisy traces mean less reliable event detection and less accurate measurements. If you increase the averaging time, it will reduce the noise in traces and improve your event detection and measurement accuracy. But of course, your test time is longer. And there are diminishing returns. Every time you double the averaging time, it improves your dynamic range by about 3/4 of a dB. So if I go from 1 second to 2 seconds of averaging time, I'll get a 0.75 dB improvement. But then I have to go 2 seconds to 4 seconds to get the next 3/4 of a dB, then 4 seconds to 8 seconds, 8 to 16, 16 to 32, 32 to 64, and beyond that, I'm up to 2 minutes of averaging time. So, like I said, diminishing returns. Takes longer and longer to get that next 0.75 dB improvement. So, launch and receive cables. Why use a launch cable? So the idea here is that you have an optical connector on your OTDR. If you want to measure the quality of the connection to the network under test, you want to separate the OTDR connection from the connection to the network under test so that the length of the fiber connecting your OTDR to the network under test exceeds the dead zone for the pulse width that you're using. We typically recommend a 150-meter launch cable. We used to recommend much longer launch cables before we offered multi-pulse acquisition. So if you were testing a very long network, let's say, a 60-kilometer network in the outside plant, then you might need 500-meter, 1,000-meter launch cord. Now with smart auto capability, we'll test the network close to the OTDR using narrow pulse widths. And once we begin to use the wider pulse widths, we've already characterized the network close in. So we don't care about the dead zone at the OTDR when we're using our wider pulse width. So with smart auto mode or multi-pulse acquisition, you can generally use shorter launch cables. You may also want to use a tail cord. A little bit more about that in a minute. So the benefit here of the launch cable is it does allow the loss and reflection of the connection to the network under test to be measured independently of the loss and reflection at the OTDR. If you used a short jumper rather than a launch cable, your first connector could be in the OTDR's dead zone. If you use a launch cable that is shorter than the OTDR pulse width, your first connector could still be in the OTDR's dead zone. So why use a receive cable or a tail cord? Oftentimes the user or customer may require the quality of the connection at the far end to be measured. And if you leave that connection open, you have no way of qualifying either the loss across a mated connection because it's not mated, and if it's an open UPC connection, you'll get a 4% reflection off that, a minus 14 dB reflectance. That would appear to be a failing reflectance, it really doesn't give you a good indication of how good that connection is either. So if you need to measure the quality of the far end connector, then you'll need to put a tail cord on. And again, the length of the tail cord would need to exceed the dead zone of the widest pulse width you're going to use to qualify that far end. The drawback of using tail cord is you've just taken the single-ended test and you require another person at the far end to place that launch cable, to connect that launch cable, clean and connect that, not launch cable, receive cable or tail cord. So configuring the length of launch and receive cables, once you've connected one up, you need to inform the OTDR that you do have a launch cable in place and what its length is. So this is one of the settings that you would configure. You want your launch cable length to be 3 to 5 times the shortest pulse width you'll be using, and 1.5 to 2 times if you're using longer pulse widths. Your OTDR distance measurement should be reported as 0.0 at the end of the launch cable. So if you use a 150 meter launch cable and you've configured the FlexScan OTDR to indicate the presence of a 150 meter launch cable, 0.0 meters or 0.0 feet won't be at the OTDR, it will be at the launch cable connection to the network under test. If you misconfigure your launch or receive cable lengths, then you will that will result in an incorrect length measurement for the network under test, and it would then also result in incorrect location of splices, splitters, faults detected in that network. So let's talk about interpreting the OTDR trace, the LinkMap, and the event table. So the OTDR trace is shown here. Connector pair will have a reflective spike, a fusion splice or a Macroband at a fusion splice will show as a drop in the backscatter level. The time it takes to recover from the spike at a mated connection is the dead zone. And if you have a poor connection, you'll end up with a longer dead zone, a long recovery tail from what's probably a saturated reflection. The end of the fiber, if it's an open UPC end, you'll get a big reflection there and then recovery tail down into the noise floor. If it's an APC angle polish connector, you'll get no reflection or a very small reflection. You can identify the distance to the event using the horizontal axis and the distance to the end. So if you want to make measurements on the trace, you can do that usually by placing 2 cursors, an A and a B cursor. And in the example below here, I've shown the A cursor placed at the start of the network. The pink shaded region is an internal launch cable inside the FlexScan. And the B cursor is placed at the end of the network where we have a reflective spike and then a drop down to the noise floor. If you have a launch cord, then you would want to place the cursor A at the launch cable connection to the network under test. And you place it just before the reflective spike from that connection. So you're measuring the backscatter level just before that connection. That means that your insertion loss measurement will include the loss of that first connector. When you place the B cursor, if you have an open-end connection, then you want to place the B cursor just before the end event. And because after that open connection, we just drop down to the noise floor, you can't measure the loss across that open connection. So now your end-to-end loss would include the loss of the first connector, but would not include the loss of the end connection. Again, if you wanted to measure the loss of that end connection, you would have to attach a tail cord, and then you would place the B cursor after the reflection has, at the end event, has recovered to the backscatter level of the tail cord. 2-point loss measurements can be useful for giving you a quick indication of the loss across a connector or a splice. In this case, you would place one cursor before the event and the B cursor after the event. As you can see, the traces here have some noise on them, and if you move those cursors just a little bit, you would see your loss measurement changes. So one of the limitations of 2-point cursor measurements is they're subject to noise. They'll give you a rough indication, but you'll see some variation. The larger the noise, the larger that variation would be. The location of the event corresponds to, in the case of a reflective connector, the rising edge of that reflective spike. In the case of a non-reflective loss due to a splice or a macroband, the location of the event corresponds to the inflection point at which the backscatter, turns down due to the loss of that splice or the macroband. Event loss is the difference between the backscatter level at the A and B cursor positions when you're making these 2-point loss measurements. It's a fast, easy manual measurement method, but it's subject to some error due to noise. And also, if you're using a very wide pulse width, your 2 cursors may be spread well apart, and your loss measurement would include loss due to the fiber itself between those 2 cursor positions. An LSA line fit, least squared approximation line fit, using the 5 cursor method provides you with a more accurate loss measurement. In this case, 2 cursors are placed before the event and 2 cursors placed after the event, and software will automatically fit a line to the backscatter level before and after the event and give you a much more accurate, it in effect averages out the noise. The line fit before is extended out to the start of the event, and the line fit after is extended back to the start of the event. And then the difference between the 2 lines at the start of the event itself is your loss measurement. And this will give you more accurate loss measurements on noisy traces. Because we're projecting the line fit to the start of the event, it also corrects for fiber loss in the dead zone of wider pulse widths. And typically your automatic measurements in the OTDR will be based on an LSA line fit. To do this manually is a lot more complex because you have 5 cursors to place. The cursor at the location of the event itself, 2 cursors before and 2 cursors afterward. If you do this manually, you want to make sure that you have no events within the line fit region because that would skew the slope of that line. So detecting and measuring macrobands, as I had mentioned before, you must test it using at least 2 wavelengths, typically 1310 and 1550, a short wavelength and a long wavelength. And in this example here, you'll see that when we tested this network, there was no apparent loss at about 1,050 meters at 1310 nanometers, but there was a half dB of loss at 1550 nanometers and 1.5 dB of loss at 1650 nanometers. So this really shows the effect of the macroband at that location and drives home the point that by comparing event loss at the longer wavelength to the event loss at a shorter wavelength, you can detect and identify whether loss is due to a macroband or a poor splice. If this was just a poor splice, we would see similar loss at both 1310 and 1550 or at all three wavelengths. Newer OTDRs today include an icon-based LinkMap with an event table. I've shown here a FlexCam LinkMap, and this gives you a thumbnail view in the top that shows your overall network with proportionally spaced events. The first icon is our overall fiber status, and then subsequent icons identify the type and number and pass-fail status of the events detected in the network itself. By selecting our table view, in the case of the, if the summary icon is selected, we get our link loss, our link ORL, and our loss per distance for the entire network. If we look at our icons, you know, here we see a passing connector, a failing connector, and a passing splice. And if we select a specific event, in this case, I've selected the failing connector, and now I can see in the event table, I can see that this failed because my loss at 1310 is 0.7 dB. That exceeds the pass-fail limit of 0.5 dB that was used in this case. My 1550 loss is okay. My reflectance at that connector is okay. So this would be an indication of probably a dirty or damaged connector. So I'd want to inspect, clean, and remate those connections. The left and right arrows allow me to navigate to the previous or next fiber section and event. And for the fiber sections, I can get the loss of that fiber section, the loss per distance, and the cumulative loss to the end of that section. The OTDR will generate an event table. Some things to be aware of is because the signal to noise ratio, there's always noise on our trace. That does mean that our event analysis cannot be perfect, and you'll see some variation if you were to test the same network several times, and that will be true across every vendor's OTDRs. So saving, downloading, and reporting OTDR results. Your OTDR test results, we recommend they should be saved in a Telcordia SOAR file format. This is the only standardized format supported by all OTDR manufacturers. The SOAR files will include your OTDR test settings, the event table, and the trace data. The SOAR standard does allow vendor proprietary extensions, so information that the SOAR standard doesn't specify how to capture may be included by the various OTDR vendors. And examples of that could be the event type, such as this is a splice or this is a connector, the presence or absence of macrobands, whether the event passes or fails against user settable limits. SOAR files can be read by trace viewers and reporting software. We, of course, offer trace viewer and reporting software, but there are other viewers and reporting tools available. Saved SOAR files can be transferred to the PC in a variety of ways. You could save them off to a USB memory stick and then plug that into your PC. You could download them via USB cable. You could transfer them via Bluetooth or via Wi-Fi. And then PC-based software supports offline analysis and reporting, allows you to view and analyze the traces, compare multiple traces, correct misinterpreted events, delete false events if you have any, bidirectionally average the traces, and generate reports. So bidirectional averaging, when and why? As you know, you could miss events at the far end of long fibers because the pulse width isn't wide enough or you don't have enough dynamic range. By testing from the other end of the fiber, you'll pick up those events that were missed, from testing from the near end. Also, in the case of a mix of fiber types in your network under test, you can have one fiber with a low backscatter coefficient connected to a fiber with a higher backscatter coefficient. And at that point, the OTDR will show actually what we call a gainer. It looks like we're getting more light back after that fusion splice instead of less light. And of course, we intuitively know that anytime you transfer light down the network, you're not going to get gain, you're only going to get loss. That gain, that apparent gain that the OTDR sees, will be offset by an excess loss at a splice to a fiber that has the same characteristics as your low backscatter fiber. If we test this in one direction, the gainer that we see in one direction will be an excess loss in the opposite direction. So if we can bidirectionally average, we'll average out the excess loss with the gain and be left only with the true loss across that splice. So many network service providers or contract installers will be required to do bidirectional OTDR testing to get more accurate splice loss measurements when verifying a new installation. So with that, I'll wrap it up and turn it over, I think, back to Charlie for any questions that might have come in.
Great, thank you, Michael. Thank you very much. We did receive a large number of questions and we are right at the top of the hour. We're actually about to go over, so we're not going to have time to answer them. But the first one I will answer, a number of people asked, is how do we get a copy of the presentation? So this will be sent out tomorrow, so stand by for that. We will send out an email with the link. So thank you, Michael, for your presentation, and thank you everyone for attending today. Don't forget, the second part of this webinar series is coming up on April 23rd and is titled From Glitches to Glory, OTDR Problem Solving Strategies, and is a great follow-up to today's webinar. An email reminder will be sent out to you next week with the registration link. So a survey will pop up as we end here, and we appreciate all of your comments on this and future webinars. A link will also be sent out tomorrow to the recording for viewing, along with a certificate of completion. And again, we will go through your questions and get back to you with answers on them. Thank you very much for submitting them today. And we look forward to seeing everyone for part 2 on the 23rd. Have a good day and a great evening, everyone. Thanks again.